Now, in the next question, it says, without actual division, find the following rational numbers as terminating decimal expansion. So first thing that we have to do without actual division, right, is to write this number in the form of P by Q such that P and Q have no common factor. That means they has to be co-prime. By that, I mean to say that if it can be reduced, P and Q, reduce it to write down in the simplest form. And then find the prime factorization of the denominator, that is Q. If the prime factorization of the denominator is in the form of 2 raised to the power m into 5 raised to the power n, where m and n are whole numbers, then we say that it is terminating. Right. But if it has factors, like if it has factors other than 2 and 5, so then it is we say non-terminating repeating. So let's begin with the first one. In the first part, it is what? 13 over 80. So if I write this number 13 over 80, it cannot be reduced. Here Q is what? Q is 80. Let's find the prime factorization of 80, which is what? 2 raised to the power 4 is 16. No, 2 raised to the power 4. Yes, 16 into 5. Now check here. Our prime factorization of Q here, that is 80, is in the form of this. Well, here I mean to write 80. Right, this is 80. So we'll say that this is terminating. The first one is terminating. Now checking for the next one, that is, it is 7 over 24. So if I write 7 over 24, here what is Q? The Q after reducing, it cannot be reduced, so it's 24. And prime factorization of Q is 2 raised to the power, that's 4. Yes. So 2 raised to the power 2 is 4. 4 into 3 is, no, wait a second. Let me write on 2 into 6, 2 into 3. Right. So it is actually, here this is 24 is 2 raised to the power 3 into 3 raised to the power 1. Now check over here. What you can see that, look into this. It has factor other than 2 and 5. So we'll say it is non-terminating recurring. So this is non-terminating. Now next is 5 over 12. Well, this is also non-terminating. As we just did, 12 can be written as what? 2 raised to the power 3, which is 4 into 3. So you can see that it has factor, right? Other than 2 and 5. So it's again non-terminating. Next, it is 35, right? So it's already in the reduced form. So similarly, if I write 35, it can be written as what? 5 into 7. So here too we have factors other than 2 and 5. So we'll say that it is non-terminating recurring. Next, it is 16 over 125, the last one. So this is 16 over. So if I do the prime factorization of 125, it's what? 5 raised to the power 3, right? So it will be terminating. Now you may say there is no 2. So we consider 2 raised to the power 0 as well. Right. So the concluding point is that if you do the prime factorization of denominator, and it have factors only 2, right? Only 2 or only 5 or some combinations of 2 and 5 both, then we say it's terminating decimal expansion, else it is non-terminating recurring. In question number 1, it says, what are rational numbers? And give 10 examples of a rational numbers. So first we need to define what is a rational number. So what does it says? The rational number definition says that any number or a rational number which can be written in the form of P by Q. So any number which can be written in the form of P by Q, where P and Q are what? P and Q are integers and Q is not equal to 0 are called rational numbers. So as for the examples are concerned, what example we can give? I can give 0 as a rational number. I can write 7 over 4, whether it's a proper or improper fraction. Even 4 over 7 is a rational number. minus 13 by 6 is a rational number, minus 6 over 11 is a rational number. Make sure you write this in the form of P by Q such that P and Q does not have any common factor. In fact, 1 is a rational number. Why so? Because 1 can be written as 1 by 1. Similarly, you see I have taken 0 as a rational number because 0 can be written as 0 over 1. But then 1 over 0 is not a rational number. Why? Because here Q, if you see Q is 0 here. So we know that Q should not be 0. So this is what, and you can give more example. Although they have asked for 10, you can write any number. Let's say I can write 17 over 6. I can write 5 over 4. I can write 3 over 2. I can write. So these are the examples of rational numbers. Let's move to the next question. So in this question, it says express each of the following as fraction in the simplest form. That means we have to write this in the form of P by Q in the simplest form. Now, if I take the first question over here, this is actually 0.3 bar. So what we can do here, let's say, we take x, right? So x is equal to 0.3 bar. Now check here what I can write this as. Can I write this as 0.333, right? String of 3 and mark it as equation 1. Now next what you are going to do here is to see how many digits are repeating. As you can see in the repeating block, there is only 1, 3, right? One digit is repeating. So we are going to multiply 10 on both sides. So multiplying 10 on both sides, it comes out to be 10. On multiplying 10 with this, you know that the decimal will shift 1 places to the right, and you can continue to write as much 3 as there on the other string. Now we are going to subtract first equation, right? First from second, right? So what is 10x minus x? 10x minus x would give you how much? 9x. And this whole string, when subtracted, will give you 0. Finally, it is 3 minus 0, which is 3. So x comes out to be 3 over 9, which can further be reduced as 1 over 3. Right. That will be the answer. Now, after this first part, I should take the second one. So here, so that you can compare and find out, here I'm going to take this, let x is equal to 0.34 bar. Now check here, this is in the repeating block. It is 3, 4, 3, 4, 3, 4, and I should mark this as equation 1. Now here, how many digits are repeating? There are 2 digits, right? 3, 4 is repeating. So instead of multiplying by 10, I'll straight multiply by 100. Now here the reason for this is we want this 3, 4 to come before the decimal. So it's going to be 3 this will come as 3, 4 point. I can continue to write 3, 4, 3, 4 as many times. So I wrote this as 3 times. So here too we'll be subtracting the first equation from the second. So that results to give you how much? This is 99x is equal to 34, because this and this will get, on subtracting, will become 0. So now we can say from here x is what? 34 over 99. Well, I can see that this cannot be reduced further, so we may leave this part as the answer for this part. Now next I'll do this one, the fifth one. So here what is x is equal to? We'll take let x is equal to 0.324. As you can see, this 324 is forming a string. Or let's say first I write this only. So I can write this x as what? This is 0.324. As you can see, the bar is over 324. So the repeating block is 324 only. 324, and marking it as equation 1. Now check here, how many digits are repeating here? There are 3 digits there in the repeating block, right? So here we'll be multiplying with 1000. So on multiplying with 1000, this is 1000x is equal to, this will come before. So it's going to be 324 point, as you know that on multiplying with 1000, the decimal place will shift 3 places, right? 324. And marking it as equation 2. Same as all such cases, we are going to subtract here. So we are going to subtract this first from the second. So what is this minus this? Has to be 999x. And this is 324. So x comes out to be 324 divided by 999. So this is 4, 5, 6, 7, 8, 9. It's divisible by 9. So let's reduce it by 9. So what we know here that 999 is divisible by 9 and 324 is also divisible by 9. So this is 3, 9, 3 times 27 and 6 times. And this is what? 1, 1, 1. I can see that these two are also further divisible. This is 3 12 times. And you should know that 1, 1, 1 is also divisible by 3 by 37. So the answer for this part is going to be what? 12 over 37. As we know, we have to write them in the simplest form. Now, I'm going to do the sixth part now. Now, what is the difference between this and the other question? What you can see that whatever the questions we did, like we did question this, we did this, we did this one. Now, everywhere the bar is over all the digits over after the decimal. But in this case, you can see that the decimal is over 7 and not over 1. So if I take this, let's say if I take let x is equal to 1.7 bar, so I can write x is equal to what? 1.777. Oh, I made a mistake. This was actually 0. So let x is equal to 0.17. And the bar is over 7. So I can write this as 0.1777, any number of 7, and mark it equation 1. So now what you can observe here that these digits here, the repeating block is clearly 7, right? And this 1 is not in the repeating block. So I have to bring this number to the left of decimal, and clearly this can be done by multiplying with 10. So it's shifting the decimal 1 place to the left. It's going to be 1 point and other. As you can see, this will come 1 over this side. So it's 7777. And this is equation 2. Now we'll multiply once again by 10 to the second equation. So multiplying this by 10, it is 100. This becomes 17 point, and we can continue to write 7777. This is fourth. No, this is third equation. Now we'll be subtracting. This time we'll be again subtracting the last two. That is second equation from the first. So what is 100 minus 10? That is 90x. And this is 16. So x comes out to be what? 16 over 90. Yeah, it can be reduced and be written as 8 over 45. Now check if I do one more. Let's say if I do this one. This time we have x is equal to what? This is 0.163, and the bar is over 63, so it should be 6363 and so on. I'll mark it equation 1. Now the repeating block over here is what? 63, right? The repeating block is 63. So but 1 is not in the repeating block, so I must multiply with 10. First I'll multiply with 10 so as the 1 which is not a part of the repeating string should come before the decimal. And then we'll continue to write the other numbers like 63, 63, 63, dot, 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 marking it equation 2. Here onwards, it should be taken as a new question where there are 2 digits repeating, right? So in the repeating string, there are 2 digits. So we'll multiply by 100. Why 100? Because there are 2 digits repeating. So on multiplying 100 to the previous case, like multiplying 100 to 10 is what? 1000. And multiplying 10 to this 63 will come before the decimal. So it's become 163 point, and we'll continue to write 63, 63, 63. Make sure you give dot, dot, dot here, showing that it continues. Now here too will be subtracting. The subtraction will be, as usual, the last two. So if I subtract the 10x from 1000x, how much it is? 990. X is equal to, and this is what? 160. Yeah, 162, right? Because 163 minus 1 is 162, and this will vanish. So now we have x is equal to 162 divided by 999. This is 617 plus 89. Yes, it is divisible by 9. So we'll be dividing 162 by 9, same as the previous. So it's divisible by 8 times. 18 times, sorry. 18 times, and this is by 111. These two are divisible by 3, right? So it's 3, 6 times, and again 111 is also divisible by 3 by 37 times. Yes, so the answer for this part comes out to be 6 over 37. So they are in the form of fraction, or we say in the form of p by q. The next question, it says write whether the given statement is true or false, and we have to give reason for this. Now, if I see the first question, it says every natural number is a whole number. So look into this. These are what? Natural numbers, right? And the natural numbers are included within the whole number, right? One more time, you can see that if I take this whole number, right, the natural numbers are inside the whole number. So we'll say, yeah, this is true. This is true. And what reasons should we give? We can give here that uh, natural numbers, sorry, whole numbers include all natural numbers, including 0. And that's why plus 0, right? So you can see that all natural numbers and 0 together is called a whole number. So the first one is done. That's true. And the next, if I see the second part, it says every whole number is a natural number. So that's not true. As you can see that from here, if you see 0 is what? 0 is a whole number, but this is not a natural number. So we'll say this is a false statement. The third part, it says every integer is a rational number. Yeah. So rational number, as you can see, this big circle includes what? Rational numbers, and you can see integers are within that circle. So this is a true statement, right? This is a true statement. And what reason you'll give that? The numbers like these integers, whatever these integers, can be written in the form of p by q, like -9 can be written as -9 over 1. Since it can be written in the form of p by q, therefore we say that they are rational numbers. Now, the next, it says every rational number is a whole number. That's not true. How can we say that this is a false statement? For that, you have to give an example. So you can see that 7 by 8 is a rational number, but it is not a whole number, right? So this is what example you can give. Now coming to the next, that is every terminating decimal expansion is rational. Every terminating decimal expansion. For that, let me bring one flow. The next question says that every terminating decimal is a rational number. So look into this flow chart. We know that decimal expansion of any number can be either terminating or non-terminating. So if it is terminating, then it is, one more time, if it is terminating, then it's going to be a rational number. As you can see, terminating, if it is terminating, then it is a rational number. So we'll say yes, if it is terminating, then it is a rational number. But if it is non-terminating, then two cases arises, that is repeating and non-repeating. So if it is repeating, then we say again it is a rational number. Now coming back to the question once again, the question here is every terminating decimal is a rational number. Yes, if it is terminating, it has to be rational. So we'll say this statement is true. Now coming to the next part, that's important. It says every repeating decimal is a rational number. Look into this. Repeating is this, right? So you can see that in the flow chart, if it is repeating, it is rational. So we'll say that. So a terminating decimal is also a rational, and if non-terminating, then repeating. If non-terminating, then repeating or recurring decimal expansion is also a rational number. Now, this question one from now exercise 1C, it says what are irrational numbers and how do they differ from the rational numbers? We have to give examples for this. So if I write the definition of a rational number, so what are rational numbers? Sorry, irrational number, not rational. So answer for this is irrational number is a number which can't be expressed as a terminating decimal expansion or a reoccurring decimal expansion are called irrational. Let's see, this flowchart will help you understand. We see that decimal expansion of a rational number can will be if terminating, then it is rational number. If non-terminating but repeating, still it is a rational number. One more time, decimal expansion of a number, if it is terminating, then it is rational. If it is non-terminating but repeating, still it is a rational number. So what is therefore what are irrational? If it is non-terminating, non-repeating. So we may simply say that if the decimal expansion of a rational number of a number is non-terminating and non-recurring, then we say it is an irrational numbers. Now the later part it says, if I read it again, it says how do they differ from rational numbers? So we may simply say that in case of rational number, the decimal expansion is either terminating or non-terminating, repeating. Now, there is another way by which you can say this, define it. You can say that any number which can be written in the form of P by Q, where Q is not equal to 0 is rational, and those which cannot be expressed in the form of P by Q are irrational. Now, some examples they have asked, so we can say like root 2 is irrational, root 3 is irrational, and pi is an example. This is pi. Pi, root 7. These are rational. Root 16 is not rational because you know that root 16 is 4, right? So we'll say that the examples is what I have given. So you can give these examples. Now coming to the next question, this is question number 2 now. It says classify the following numbers as rational or irrational. We also have to give reasons to support the answer. Now, if I take rational numbers, so you should understand any number which can be written in the form of P by Q, where Q is not equal to 0. Another way we can say that those numbers whose decimal expansion, if terminating, then rational, and non-terminating, repeating, still it is rational. We'll be using these two ideas to determine which of them is rational. The first one is under root 4. We know that under root 4 is what? It is equal to 2, and 2 can be written in the form of P by Q. So this is rational, right? I'll write R for rational here. First is rational. Now next is under root 196 is what? 14. So this is also rational. Under root 21, this is not rational, right? This is not rational. I mean, under root 21, reason being, this is not a perfect square and therefore cannot be written in the form of P by Q. In fact, its decimal expansion is non-terminating, non-recurring, right? So therefore, this is irrational. Same with under root 43. So this is also irrational. Now coming to the next, this is irrational for the reason that this part is rational, but this whole is not, right? Because you know that, let's say if I say 3 plus a non-terminating decimal expansion, right? For example, what I mean to say that if I find uh, if I write 3 and under root 3 is what? Non-terminating repeating 1.73205080 and something something. So if we add these together, we will get what? Non-terminating recurring also, like 3.7320, something like that you will get. So what you can see that 3 may be a rational, but this whole is not a rational, right? So this is irrational. Same reason why this is irrational. Now this is root 6 is irrational, and therefore this is irrational. And this is also irrational because you can see that no, this is rational because its decimal expansion is what? Non-terminating but recurring. This recurring is what? Repeating, right? 6 is being repeated, right? That's why it is rational. Coming to the next, this you need to watch. This is what? This is 2, 3, 2, 3, but then it is 3, 2. Can you see this? Right? It's not 2, 3, 2, 3, 2, 3. Let's once again. Had it been 2, 3, 2, 3, like 2, 3, 2, 3, and then another 2, 3, and so on, then it would have been repeating, right? Then it would have been repeating, but here it is non-terminating, non-repeating. So we'll say that this is irrational. Next is, if I look into the next one, this is again non-terminating, non-recurring. You see 0, 4, then it is coming as what? 004, 004. Then you see next time it is coming 0004. So this is an example of an irrational number. So this is irrational, and the what reason you will give here? That it is non-terminating, recurring, non-recurring. This is irrational. So sorry, this is rational because it is clearly terminating. So if it is terminating, it has to be rational. This is also. Now the next part. This is 356, and then you see we are getting a string 56, 56, 56. So it is terminating. Sorry, it is rational, and the reason for it being a rational because for the repeating decimal expansion. You check here, this is repeating decimal expansion. Now coming to the next one is pi. Well, pi is irrational. Pi is irrational. But 22 over 7 is rational because they are not same, right? Many of you actually take consider pi as 22 upon 7. This is not correct, right? The value of pi, we sometimes take 3.14 or sometimes 22 over 7. That's for the convenience of calculation, right? The value of pi is non-terminating, non-recurring. One more time, the pi is what? Non-terminating, non-recurring. Decimal expansion, if I talk about, and that's why we say it's an irrational number. So this is how we have done these questions.